One, two.
Because you know I'm all about that bass, no trouble. I'm all about that bass, no trouble. I'm all about that bass, no trouble. I'm all about that bass.
There we go, another version of All About That Bass. This lesson here is all about that bass, and I'm going to trainer you up in how to do them. See what I did there? That was clever, wasn't it? All right, logarithmic functions. We're talking about logarithms. All right, the definition of a logarithm. I got a lot of stuff on here that we're going to put in here, but basically a logarithm, if you're going to define it, the mathematical way, y equals log base b of x. That's how we say that officially. Y equals log base b of x, if and only if b to the y equals x. And of course, b's got to be greater than 0, b's not equal to 1, and x has to be greater than 0. So there's a lot going on right there. Now, how does Mr. Bean say that? Well, he says it the official way because he's pretty official. He says it the way that everybody's universal way to say it, so everybody knows what we're talking about, log base b of x. But Mr. Kelly has his own voices in his head. I've had him there a long time, and when I see log bx, log base b of x, actually I say it the exponent I use on b to get x. So y is the exponent I use on b to get x. And the reason I say it that way is because it makes translation so easy when we do the next part. Remember, exponential functions are of the form y equals b to the x. Logarithmic is the inverse. Inverse means they undo each other, so it's like switching x and y. So it's the same as y as an exponent on some base would equal x. That's crazy. So let's look at number one. Technically, you say it like Mr. Bean, you say log base 5 of 125, that equals 3. Okay, the way I say it, the exponent you use on 5 to get 125. So the exponent you use on 5, the base is 5. The exponent, blah, 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 is 3. So this is telling you how to write it in what we say is exponential form. That means you write it with an exponent. So 5 to the third equals 125. That is true. The exponent I use on 5 to get 125 equals 3. Whew, how about this one? Well, let's rewrite this thing. So a cube root, remember that's just, how do we write that as an exponent? This would be 1/8, and using the cube root, we'd have to raise that to the 1/3 power. That's what the cube root means. And so all that would equal a half. So using saying it the way that I normally do, I say the exponent that I use on 1/8. So I would write this in logarithmic form. Log base 1/8, because we're all about that base. The exponent I use on 1/8 to get 1/2 is 1/3. So that's how you write it in logarithmic form. Booyah! So that's those two. Let's go on. Okay, so number 3, we have to evaluate the following logs without using a calculator. Frowny face, no calculator. So we get log base 2 of 8. I would say that as the exponent I use on 2, so 2 to some exponent, that's question mark, equals 8. So what exponent is that? Well, that's going to be 3. This is all going to equal 3. Because 2 to the third. Can I put an x there? 2 to the x would equal 8, and so x would have to equal 3. I like my x's. All my x's, they're in Texas. All right, number 4. The exponent I use on 8, so 8 to some exponent has to equal 164. All right, well, what's that going to be? This is 1 over 8 squared, so this is going to be -2 on that one. You try the last one by yourself. Go! All right, last one by yourself. The exponent I use on 8 to get 1, that's got to be what? 8 to some power has got to equal 1. Well, x is going to equal 0 there. How crazy is that? That equals 0. So the log base anything of 1 is 0. You can do that. Hey, how fun is that? We're almost done with those. We're so fast. We're on number 6, expanding and condensing logarithms. Now, what's nice about these, same rules as exponents. So if you can do your exponent rules, you can do your log rules. They just look a little different. Like, here's the product. You're multiplying two numbers together. They have the same base. So the log base b of x times y, if you want to expand this, it's called, we're going to make it bigger, then you can just add those two logs together because they're just exponents, remember? This is like b to the x times b to the y. that's the same as b to the x plus y. That's the rule, right? I mean, if we were going to do this, it'd be b to the x plus y. Look, they're logs. Logs are exponents. It's the same rule. So if you're multiplying here, you can split it up into addition. If you're dividing, split it up into subtraction. And then the power property, it's the same. Well, it's a little different. Sorry. We have log base b of x to the y. We can take this thing and put it down front. And when you put it down front, you get y times the log of b to the x. Because remember the power, the product powers to powers property. What do we call that property? Powers to powers. You just multiply the exponents. Well, this is an exponent, so you can take that exponent down front and you are multiplying exponents. That's why that works. So let's look at number 6. How are we going to expand this? Well, we have log base 4 of, I see this term, we have this term, that's raised to the 5th power, and we have this term, and they're all being multiplied by each other. So the first thing I would do is I would separate them using this first rule right here, the product property. So I would say this would equal the log base 4 of 3 plus log base 4 of x to the 5th, that's one term in itself, plus the log base 4 of y. And now we're going to deal with that 5, that exponent up there. We're going to put that down front. So final answer, number 6, we have log base 4 of 3 plus that 5 is going to come down. That's using the power property. So 5 times the log base 4 of x plus log base 4 of y. All right, so that is number 6. Write that down because I'm getting rid of this because I need more room. Booyah. Okay, number 7. We'll change color up here a little bit. Change a little color. What do I see here? We have division and we have an exponent. So what I'm going to do is simplify this a little bit using our exponent rules. So this is going to equal log base 3 of p to the 5th. Remember, our rules are that 5 can go to the p and it can go down to this term in the bottom. So that's going to be q to the 20th. All right, so log base 3 of p to the 5th over q to the 20th. Now we have subtraction. That's using this rule. We're going to use the quotient property right now. We're going to have subtraction of those two different terms right here, p to the 5th and q to the 20th. So we're going to get log base 3 of p to the 5th minus, we're going to subtract using quotient property, log base 3, it's got to be the same base, of q to the 20th. Almost done. Now we're going to use the power property. We're going to bring that exponent down front for both of them. Final answer for this one. We get 5 times the log base 3 of p minus 20 times the log base 3 of q. And that is expanded for number 7. Write that down because I'm going to erase all this. I'm going to need more room. Okay, number 8 now. It says condense. That's going backwards. We need to put all this stuff together. So here we go. First thing I'm going to do, I'm going to multiply this 2 to both of these terms here. Distributive property. So that's going to give us 2 times the log base 4 of 8 minus 2 times, because that 2 goes to both, log base 4 of 5. And that second term, that's not going to change in this step. Although some of you can probably see what we're going to do now. We're going to bring those coefficients up top as an exponent. So that 2 comes up here on the 8. We're going to get log base 4 of 8 squared minus log base 4 of 5 squared, because that 2 is going to come up there. And what do you got? 0.5 power. Woo, that's ugly. So we get plus log base 4 of 25 to the 0.5 power. All right, so what does that mean? Can I work some of this out? I'm going to work some of this out, whether you like it or not. So 8 squared is 64. So log base 4 of 64 minus log base 4 of what? Well, that's 5 squared. That's 25. Plus, we have log base 4 of 25 to the 0.5. What is 20? I'm going to do this over here. 25 to the 0.5 power is the same as the square root of 25, which equals 5. So I'm just going to rewrite this part as 5. That'll make my life a little easier. All right, so what is the exponent I use on 4 to get 64? The exponent I use on 4 to get 64 is 3. So the log base 4 of 64 just equals to 3. Now I need to subtract this is crazy, minus log base 4 of 25 plus log base 4 of 5. You know what I'm going to do? I am going to rewrite these. And you're going to see why in a second. I'm going to rewrite these. I'm going to switch these two terms. So let's do that. So this is going to be plus log base 4 of 5 minus log base 4 of 25. Now, Mr. Kelly, why did you switch those? Because I think this is the easiest way as not to get confused here. This is a negative log base 4 of 25. This is positive. So I'm going to put that positive first because now we have subtraction here. And like we can use our subtraction, our quotient rule that's above right in the middle there. So we have the same base and we're subtracting. So what does that mean? That means we can divide these two terms right here. So this is going to equal 3 plus log base 4 of 5 over 25. I can divide that by this. Now, the other way, I didn't really, like, it's hard to see that quotient. That's kind of why I rewrote it. It's the same. Trust me. These will now cancel. So we get final answer 3 plus log base 4 of 1/5. And what is the exponent I use on 4 to get 1/5? I have no idea. No idea. That is not a very nice number. So we're just going to leave it just like that. Hey, we're all done with that one. Oh my goodness. Time for a break. Should I show part of that clip again? Nah, we'll just keep going. Okay, change of base rules. Remember this? Look at the only difference here. Log base C of A. You can take some log base B. It's a different log, different base log, and then you can just put the A over C, and that's how that works. So for the first one, what do we got here? So this would equal the log of 5 over the log of 12. Now remember, if there's no base there, it's a 10. So log base 10 of 5. That's a common log. All right, log base 10 of 12. The exponent I use on 10 to get 5. Well, that's ugly, and this is ugly too, so we need our calculator. So let's bust out that calculator. Okay, so here's my awesome calculator simulator thing here. And look, we have log base, there's keystrokes down here, but log base 5 divided by log base 12, you get 0.647. I'm going to round that up. We're going to go up 4 places. 0.6477. All right, so this equals 0.6477. Okay, but here's the thing. There's another way to do it in your calculator. I'm going to show you this now. Never before seen. Go show an Algebra 2 kid. They'll love you. You go to Math, and then you scroll up. See that log base? Log base. That function right there, you don't have to change the bases. We can put that right in there. So what do we get here? So this would be a 12, and this would be a 5. You can just hit Enter, and guess what? Same exact answer. That is, again, under Math, and you go up twice, and that should do it for you. So using that, find the answer number 10. Go! Pause the video. Go! Here we go. There's my answers for those. 4.3219. I would cut it off right there, and that's how you do that one. You can do it either way in your calculator, but you do have to know that change of base rule because it's going to come in handy later. Guess what? Right now is later. We're going to start solving these equations using logarithms. So 41 equals 7 to some x power. So let's do that. 41, Bean's method. We have 3 different methods. We're going to call it the Bean-Brush-Celli method. By the way, I made this up. It's 100% not true. But the Bean-Brush-Celli method, Bean's method, you take the log of both sides. So to take the log of both sides means that's going to keep it equal. So we're going to have the log of 41 is going to equal the log of 7 to the x power. Remember that x can come down front. So the log of 41 equals x times the log of 7. All right, now we can divide both sides by the log of 7, and so x is going to equal the log of 41 divided by the log of 7, and that's going to give you your answer, which up here you can see is 1.908. All right, so that's Bean's way of doing it. You take the log of both sides, but Brust, you know how he's different than Bean. They're different. They're both different. We're talking about same and different. They're different. So what Brust likes to do is he likes to cancel things out. So to cancel this out, the exponent I use on 7 to get x. What if he uses that, watch this, log base 7 of 7 to the x power. Okay, so let's read that. That says log base 7 of 7 to the x power. What is the exponent I use on 7 to get 7 to the x power? This is double talk. I'm going to say it again. The exponent I use on 7 to get 7 to the x. Well, to get 7 to the x, I have to use x. This is all going to simplify to x. Okay, well, let's back it up a little bit. So back to here. I took log base 7 of this side. I have to take log base 7 of this side as well. So this is the Bruss method. We're going to say take the log base 7. It's going to make those guys cancel. You get an x. So x here is going to equal log base 7 of 41, which you know is the same as the log of 41 over the log of 7. Guess what? You get the same answer doing it that way. That's the same as the Bean method. Now, the Sully method is graphing. Graphing's so simple. You put this in y1 and you put this in y2. Ta-da! And then you find where they intersect. You already know how to do that, and I don't need to go through all that. But when you do, you get the answer of 1.908. Guess what? That is the same answer. So you have 3 different ways you can solve these. Do number 12 all by yourself. First, take the log of both sides. That's the Bean method. Then the Bruss method. By the way, you don't have to remember that Bean is this and Bruss is that. You just have to remember how to do it. So take the log of both sides, or you can make the logs cancel, or you can graph it. Go ahead. Do number 12 by yourself. Go! Okay, coming back, you should get a -2 for each one of these as you work through. It's the same as the other one before, so I'm not going to waste your time. This is already a long video. All right, other reminders. The exponent I use on any number to get itself is always going to be 1. All right, so any base, if you're trying to log base b of b equals 1. Okay, log base b of 1, that means what exponent do I raise b to get a 1? Well, b to 0 is going to equal 1. Anything raised to the 0 power is 1. All right? Log base 10 is called the common log, and it's basically if we do log and we don't put any base down, we mean a 10. There's an implied 10 down there. All right, what else we got down here? Log base b of b to the x. We just use that. If I use the exponent I use on b to get b to the x, that's got to be x. And if you raise b to the exponent you use on b to get x, you get x. That's crazy. You have to say that a couple times to yourself. If you let's see, the exponent I use on b to get x. I'm using that exponent on b. Guess what I get? X. And lastly, remember log base e, that's called the natural log, but we abbreviate it with ln. ln of x, that's the natural log for that one. All right, so that's reminders from last year, trying to set you up for success. Okay, so let's talk about graphing a little bit. Here's my graph. Remember, this is graph of what? This would be, well, g of x. So g of x, y equals b to the x power. That's an exponential graph. So this is exponential. We learned about that in 7.1. This is exponential decay if b is less than 1 but greater than 0. All right, so these are 2 graphs here of exponential functions. And in graphing logarithmic functions, all you do is switch x and y. Look, x equals b to the y. But then if we want to solve that, we got to take the log base b of both sides. So you end up with this equation right here. Log base b of x. So that would be the inverse of this exponential equation here. So how do we graph it? What does it look like? Well, it's a reflection in the line y equals x, like all inverses are. You just reflect it in that line, and it'll show you how to do it. Now, the way I like to do it, you have to go straight at the line, perpendicular to it. So then you get a new point, like over there. This point here, I go straight. That would come over here. And then I find, like, see this point here? You got to go straight to the line. It's one diagonal square away. That's going to end up right here. We can do the same thing, like, well, nowhere. How about here? That's like in the middle. Ooh, that's going to be like, so what's this going to be? This is the point. Let's make this up. This is like -1, like a half. So over on this side, it's going to be down here somewhere. So it's going to be a half -1. That's going to be right here. So now you can see what the shape of this thing is going to be. Will it ever cross the y-axis? And the answer is no, because look, this never crosses the x-axis, so this will never cross the y-axis, and that'll maintain its symmetry. There you go. That's basically how you can graph one of these logarithmic functions. Now, honestly, most people would plug this in the calculator, go to the table, put some points down, do your best job there, but you should be able to at least recognize a logarithmic function. So how about this one here? They give you exponential. What's the logarithmic function look like? Well, you got to go straight to the line, go on the other side. So what do you got? This is asymptotic here to the, what do we call that? The x-axis, or y equals 0. So when you reflect it, the reflection is going to come up here and be asymptotic, which is totally not what that looks like. That is the worst drawing ever. Kelly sucks at drawing. Oh my goodness. All right, we're going to try that again. That was terrible. That was terrible. That was absolutely terrible. All right, so this point right here would go right here. I'm going to try to do this more. I'm going to try to do this a little more systematically. So this point goes up here. The point 0, 1 would come down here. Let's find another point. This is the point -1 and then 2. So if I switch that, I'm going to get 2, -1. So that comes down here. Now I can kind of see the shape of this thing a little bit better. Asymptotic right there. Come on, Kelly. Come on, Kelly. Come on. Pretty close. Hey, what do you expect from me? I'm not a computer. But this is basically what the inverse looks like. It's a reflection over the line y equals x. All right, that's enough of that. We're going to keep going on. We don't need to get too much into graphing here, but we do need to learn how to solve these, because solving, if you don't know what to do, you're in big trouble. So log base 10, right? It's common log of x equals this, and we want to basically find out what value of x. So like in all equations, we're going to use our inverse operations. We want to kind of make this thing cancel out. So this is, if we read it the way I taught you, the exponent I use on 10 to get x. I'm going to use that exponent on 10, but I got to do to both sides. But if I use that exponent on 10, guess what I get? X. So basically, I just need to figure out x is going to equal, this kind of looks weird now. Looks weird. X is going to equal 10 to the 3.0876 power. Now, all of your answers here are going to be kind of crazy. You're going to have to go out 4 places using your calculator here. What do I got here? Oh, right there, that bottom one. 10 to the 3.0876, you get 1223.4888. You can cut it off right there. Let's write that down. That is our final answer. Final answer. All right, so that's pretty specific there. Pretty detailed. How about the next one? Well, it's a natural log. So it's the exponent I use on e. All right, so find that one out. That's my hint to you. See if you can get the right answer. Go. Okay, so I'm just going to bring up the calculator. I figured you might want to watch this. So second natural log right there. E to the, see that little e to the x? That's going to bring you right here in the calculator. So e to the x. And in this example, what do we need there? We needed a negative 9128 ten thousandths. So how are we going to write that out? We're going to use negative 0.9128. And when we push the enter button on that, we get 0.4014. What? Mr. Kelly doing some rounding? So x equals 0.4014. Done with that one. Whew! So that's how you can use a calculator and use that little rule of, the base. If you take the log of a base and you raise that to the power of that base, they cancel out. That is crazy. Okay, so going back to what we learned before, there are 2 steps to finding the inverse. We're going to use the property of logarithms to find the inverse of the given function. So number 1, we switch x and y. And then number 2, we solve for y. Remember doing that stuff? So you switch x and y and then you solve for y. So I'll show it in red when I'm going to write the function out, y equals 4 to the x. Remember, f of x, we can just replace it with a y, and then we switch x and y. So when I do that, I'm going to get x equals 4 to the y. Now at this point, we're just going to use our property of logs. We're just going to take the log of both sides. So the log of x is going to equal the log of 4 to the y power, but I can bring that y down front. So the log of x is going to equal y times the log of 4. By the way, this is an exercise in y's, g's, 4's, and later we're going to have 9's. It's crazy. So y is going to equal the log of x over the log of 4. And that is our inverse. Now, if we want, we can figure that out as a decimal, but I'm just going to leave it like that. You cannot separate this into x minus 4. Remember, that's only if you're subtracting logs, and here we're dividing logs. If you're subtracting logs, you can then write the log of x divided by 4. That's how that rule works. You can go back up and look at that rule, but this is basically the inverse of x. And you can work this log of 4 out if you want to as a decimal, but I don't want to. I want to leave it just like that. So that is the answer to 16. Let's do 17. So substituting the y for f of x and then switching x and y. Now we need to solve for y. But one thing I noticed with 17, I have 3 raised to the 2y power. That is exactly the same as 3 squared raised to the y power, right? Because of our power properties there, our exponent properties. And 3 squared is just a 9. Okay, so this is just the same as 9 to the y power. So at this point, I can take the logs of both sides. So the log of x is going to equal, and I'm going to bring that y down right now because I know that's going to be the next step. Again, look, g's and 9s and 4s and y's. Mr. Kelly. So this is the log of 9. We're going to divide on both sides by the log of 9. So we're going to get the inverse of x, which is in this case the same as y, is going to equal the log of x over the log of 9. And that's going to be our inverse function. You try with the last one all by yourself. Here's a reminder for the last one. Remember, anything to the 1/2 power is actually a square root. Square root. Try the last one by yourself. Pause the video. Go! Okay, so solving number 18 here, we get y, or technically we get the inverse of x, same as y, equals log of x over the log of square root of 5. Because 5 to the 1/2 power is really square root of 5, that y is going to come down. You get the log of both sides, you divide by the log of radical 5. That's how we get to this point. How can you check yourself to make sure you're always right? Because some of you are OCD and want to make sure you always get it right, and that's a good thing. So we go to our calculator here. Where'd the calculator go? Okay, calculator. What do we have here? So I just graphed the original function, and I graphed my answer. And that's how I typed it in there. And so if I look at them on a graph, you notice that they are inverses because there is y equals x goes right in the middle there, and they're a reflection of each other. So they are, in fact, inverses. Okay, last two. Let's get these out of the way. Same idea. So I'm going to write down the original equation here. Y equals log of x plus 1. And from that point, we want to make it x equals the log of y plus 1, and then solve for y. So I subtract 1 from each side. I get x minus 1 equals the log of y. And how are we going to get rid of that log? Remember, this is the exponent I use on 10 to get y. So if I use that exponent on 10, so I'm going to raise each side of the equation as a power on top of 10. It's 10 to that power. They're going to cancel each other out. I'm going to get y equals 10 to the x minus 1, which in this case is the inverse of f. That is amazingly simple. Looks more difficult, actually more simple. Let's look at number 20. So we want to switch x and y. So we're going to get here the natural log of x equals 2 times the natural log of y. And I want to solve it for y. First thing, I am going to, let's see, multiply both sides by 1/2. So 1/2 times the natural log of x equals the natural log of y, right? Because the halves would cancel with the 2. And now how do you get rid of natural log? That is the exponent I use on e. So I'm going to raise e to this power. Well, you know what I'm going to do first? Let's put that 1/2 up here on x. So the natural log of x to the 1/2, right? Because that exponent, you can put it up there, equals natural log of y. Raise e to that, raise e to this. What are we going to get here? A whole bunch of canceling. We're going to get x to the 1/2 is going to equal the exponent I use on e to get y. If I use that on e, I get y. So y is going to equal x to the 1/2. So the square root of x equals y, which is our inverse function here. And that is it. Woo! Less than 30 minutes, New Year's resolution. And this is all she wrote. Game over, denied. 20 problems worked out. This has been a long one. Hey, this is Mr. Kelly in K-Town. Remember, it's all about that bass. And it's nice to be important, more important to be nice. So